All right, last section of Physics 20 is section 8.4 on the Doppler effect. Okay, so wavelength and frequency of a source at rest. So imagine a bug on the surface of a pond. Okay, so this is our bug here. Okay, the bug beats its wings once a second and causes ripples in the water. Okay, and so this is our bug beating its wings. Our ripples come out from the water. Because of the constant frequency of the vibration, okay, of 1 hertz, the waves spread out evenly. And so no matter where you are in relation to the bug, this wavelength would be the same. Okay, so if you're standing up above it, okay, or below it, wavelengths coming towards you would be equal. And so just kind of showing, so if we have a wavelength, like if we want to know our wavelength and we know that we have a 3.5 meter wave and our frequency, okay, is 100 beats a second, okay, then our wavelength, or sorry, if we know our speed and wavelength, we can find our speed and frequency, we can find our wavelength. And from there, find our frequency. Okay, now let's say that the bug beats its wings at the same frequency, but while moving to the right at a constant speed. So as you can see, as it's moving to the right, the wavelengths in front of it actually get closer together. Okay, the wavelengths behind it get more spread out. Okay, and just kind of showing what's happening here. So again, like it starts here as it moves forward. Okay, the direction of movement's this way. Our wavelengths get smaller. Okay, and then our shorter wavelengths, okay, which changes our frequency and so on. So if the source is moving towards a listener, the apparent frequency is a higher pitch. Okay, because if we decrease our wavelength, our frequency is going to increase. Behind it, if someone was standing behind it and listening, okay, the source is moving away, so the apparent frequency is lower pitch. Okay, again, our wavelength's larger, so it's going to decrease our frequency. Okay, so the greater amount the Doppler shift in the reflection of the wave, the greater the speed the car is moving. Okay, and so this is how radar guns work for police. Is they send out a radio signal at a certain wavelength, okay, and then the car reflects it at a different one. Okay, analysis of their Doppler effect. Okay, our formula we can use. Okay, so the frequency, okay, our Doppler frequency in hertz is equal to the velocity of the waves in meters per second. So that's our velocity of our waves. Okay, the velocity of the source, okay, in meters per second, that's here, okay, times the frequency of the waves emitted by the source. Okay, sources that are moving towards you, we use the minus sign. And if source is moving away from you, use the positive sign. Okay, and so it's always going to be your velocity of your wave over, if it's moving towards you, the wave velocity of the wave minus the velocity of the source. Okay, over here it would be plus. Okay, when things are breaking the sound barrier, so if you've ever seen the Jets or anything break the sound barrier, if you've gone to air shows, okay, if something's going slower than the speed of sound, pressure moves. The pressure moves out of the way and it moves around. Okay, at the speed of sound, the pressure waves at the nose form a shock wave. Okay, they all stack on top of each other. Okay, so at a supersonic speed, the shock waves form a cone, resulting in what we call a sonic boom, where the waves kind of compress, okay, and you get past the speed of sound. Okay, so again, reading pages 429 to 434, or even better, watch some of the videos. Again, if you aren't sure, go on YouTube, type in Doppler effect. You're going to find lots of different videos. Okay, you can also check out, like, there's a couple different videos from different physics instructors. Just type in like Physics 20 Alberta, and there's a couple different instructors that have all their notes up that might be more in depth than mine.